Thank you for inviting me for this talk here today. I'm Suraj, finally a PhD student at UIUC, and today I'll talk about my PhD research work titled Scaling Data Rates, User Density, and Sensing Resolution in Next Generation Wireless Networks. I'm happy to take questions in the middle of the talk, and especially for the online audience, you can either type in the questions in the chat or even interrupt me during the talk. That's totally okay. All right, so next generation wireless networks will enable many new applications, such as wireless VR and AR, self-driving cars, space communications, precision agriculture, and on-chip networking for high-performance computing. And not only will it enable new applications in the communication sense, it will also push beyond that to achieve joint communication and sensing over the same network. This is, in fact, a central vision in 6G, where you want to use the communication signals to do localization and imaging as well. And there's been a lot of push towards this vision from both academia and industry. And to enable all of these applications, a central technology is going to be millimeter wave, where we transition to operation in these very high frequency bands, specifically the millimeter wave band here. Now, the advantage of moving to millimeter wave is that we get access to this huge amount of bandwidth that we just did not have before. And this allows us to do new things with wireless links now, such as enabling wireless communications at multi-Gbps data rates, and also hyper-precise localization and vision-like perception, because your sensing and imaging performance is going to be proportional to bandwidth. If you consider the region of the spectrum where we've been operating today, we are in this tiny chunk below 6 gigahertz, where you just don't have the available bandwidth to allow for such capabilities. However, while millimeter wave has all these advantages, it also comes with some major challenges. And the big challenge with millimeter wave is that as you go higher in frequencies, your signals start to attenuate a lot. And as a result, millimeter wave radios need to use these phased array antennas that can focus the power of your transmissions in a particular direction towards your client. Luckily, because the wavelength is high, because the frequency is high and the wavelength is small, you can actually pack many antennas into a very small space, and you can create very narrow pencil-like beams. And this shift to directional transmissions totally changes the way wireless networks operate. To show why, let's consider today's example where these networks are broadcast. So that is the signals propagate in all directions. So as a client, no matter where I'm standing, I'm going to receive the signal from my access point. However, now with millimeter wave, because your transmissions are directional, as a client, I will not receive the signal unless I am in the direction of the beam. And if both AP and client are directional, then you first need to align the two beams towards each other to communicate at high data rates. And as the client moves, you need to keep realigning these beams. And this directionality is precisely why we have so many issues in millimeter wave networks, especially when it comes to things like mobility and blockages that lead to unreliable connections. And this directionality is also the reason why we see all these different reports that say that millimeter wave 5G is still not performing as well as promised. Now, of course, there's a lot of research going on how to address these challenges. And while most of the prior work looks at how can we make a single millimeter wave link more reliable, in my research, the central question that I try to tackle is, how do we scale these millimeter wave technologies reliably beyond just a single link, while at the same time also adding new functionalities in these networks to enable robust imaging and sensing capabilities. And towards this end, I've built several systems and protocols in my PhD. So for instance, towards scaling millimeter wave networks, one of the first systems that I built is called BounceNet, where we built a protocol that can enable extreme dense spatial reuse in millimeter wave wireless LANs to allow many users and clients to transmit simultaneously without interfering. And this helps scale the network throughput with the number of clients. We followed up on this work where we showed that if you can further modify the antenna beam patterns at the physical layer, you can actually eliminate interference altogether. And in this paper, we showed the first practical null steering system for millimeter wave networks. And I've also explored the space of millimeter wave on-chip networks, where essentially we designed a protocol that leverages deep reinforcement learning tools that can generate new MAC protocols to be deployed on the on-chip wireless networks in multi-core processors. And essentially, these new protocols are optimizing and adapting to the highly dynamic traffic that you see on on-chip wireless networks. Yes. Yes, so I will be talking about the hardware in each of these projects, but mainly it is SDRs at the baseband, and we have millimeter wave RF front ends. There are a couple of companies like Pasternak, Sivasima, where they all provide the RF front ends, some with phased arrays, some with horn antennas. But I can get into the details at the end. Yeah. But I will show slides with the hardware setup and everything that we did use for all these experiments. Okay. So apart from our work on scaling communication systems, I've also done work on sensing and imaging for wireless networks. And one of the first projects I did here is building a millimeter wave radar imaging system that can generate very high resolution and perceptual images of the environment, even in dense fog. As you can see here, in fog, cameras completely fail, whereas although radars work, they give you extremely low resolution, and you can't say what the object being imaged here is. Our system, on the other hand, can take as input these radar images and produce images that are perceptual to humans and can work even in dense fog. And I was also awarded the Qualcomm Innovation Fellowship for this work. And lastly, I've also done work at the intersection of networking and sensing, where we essentially want to use communication signals to do joint communication and sensing. And in this space, I built a system called ISLA, where the goal is to leverage the high bandwidth of 5G signals to allow high resolution ambient localization for IoT devices. And the idea here is the IoT devices will only overhear 5G signals, and we do not need it to coordinate with the 5G base stations or even modify the 5G base stations in any way. This is completely ambient. And lastly, I've also done work in collaboration with Microsoft Research, where I was working on the FarmBeats project, where the high-level goal is to design an AI and IoT platform for data-driven agriculture. And in this project, my work was to design a very cheap RF-based wind sensor that can essentially modulate ongoing IoT communications on the farm and sort of physically modulate wind information on top of these existing signals. I was also fortunate enough to be able to present a demo of my work to Bill Gates during his visit to our deployment site in Washington. So this is a summary of my research contributions. And the overarching goal over here is, how do we scale the system performance of millimeter wave networks, either in terms of number of users and network data rate, or in terms of sensing resolution and imaging performance. And in order to address these different challenges, most of my work mainly innovates at either the MAC or the PHY layer of the millimeter wave network stack, and also by finding connections across different disciplines of computer science and electrical engineering, where I've either used tools from other areas like AI, vision, RF circuits to solve wireless problems, or I've used wireless technologies to solve problems in other domains, such as parallel computing, high performance computing, and so on. So in this talk, I'll mainly focus on a few of my projects here, but I'm happy to take questions about any of the other projects as well at the end. So I'll start with BounceNet, where the goal is to design a wireless LAN network that can scale the network throughput with the number of clients. And you can take this back to the VR example, where you can have multiple VR users in a room and they're all playing a multiplayer game. But even if new clients come in, you don't want the data rates of existing clients to drop. So how do you scale the throughput even with the addition of new clients? And the opportunity for scalability comes because of the directionality of the radios. Now, I did mention that directionality brings a lot of challenges, but at the same time, it also brings this new opportunity for scalability. So you can see here, because your transmissions are directional, there is potential here to add more access points on the same frequency such that they can all communicate without interfering. And if we can do this, we can actually also scale the network throughput of the entire system by adding more and more access points. And because of the directionality, all these users can still transmit and receive without creating any interference between the links. However, note that both the access point and the clients are directional. So to be able to communicate at high data rates, you first need to align the beams of each of these links towards each other. And the main question that I'm interested in here is, if you have such a large network with many, many links, how do you align all the links of, how do you align the beams of all these different links? Now, of course, there's been a lot of past work on how to quickly find the best beam alignment for a single link in a millimeter wave network. However, we have shown that when you have a much larger network with many links, you can't directly apply such single link alignment schemes. That is, each link cannot align the beam independent of what the other links are doing in this network. And to see why, so multi-link beam alignment is challenging. And to see why, let's consider this example here, where you have these two access points and two clients. Now, if you were to simply apply one of the past techniques for single link alignment from literature, then both the access points would simply align along the direct line of sight path, which is technically the individual best paths, but this will lead to interference and the network throughput will drop. But the situation here is actually even worse. Because the transmissions of the APs are directional, this means they cannot hear each other's transmissions, which means they cannot even carrier sense to avoid interference now. And in fact, it is quite well known that carrier sense does not work in directional networks. Moreover, you could also have the situation where one of the access points is actually transmitting in a completely different direction. Even then, you could have situations where the signal bounces off some reflector in the environment and creates interference due to multipath. So the point here is that we cannot align the beams of each AP and client independent to what the other links are doing in this network. And towards this end, in this paper, I present BounceNet, which is a many-to-many beam alignment protocol that can enable many links to operate in parallel without interfering, and as a result can scale the network throughput with the number of clients. And the key question to solve in BounceNet is, how do you find the best alignment of beams that can densely pack as many links as possible? And to do this, our key intuition is we are going to leverage the sparsity of the millimeter wave channel. Now, let me explain what I mean by this. In millimeter wave networks, it is pretty well established that there are only a few propagation paths between any transmitter and receiver. And this is because the path loss is so high in millimeter wave networks. So this means that there are only a few paths between the transmitter and receiver. And because you have these extremely narrow directional beams, you can actually pick which path to route your signal through. So for instance, I could exclusively decide to send my signal along this line of sight path, or I could choose to send it along this indirect path through the reflector. And now what this allows us to do is physical signal routing, where we can pick which path to physically route our signal through, given all the different air paths in the environment between the transmitter and the receiver. To see why this is useful, let's go back to our previous example here. So here we had a situation where if both the links just aligned along the best path, they interfere, and it leads to the network throughput dropping significantly. However, if AP2 here could instead send its signal off some reflector in the environment, it could now communicate along this indirect path, and both of them can still communicate simultaneously without interfering. This leads to a much higher network throughput, total network throughput, compared to if they both just naively align along their respective best paths. So this is a clear example of how physical signal routing can lead to more efficient beam alignments in large networks. Next, I'll show you how we are going to leverage this idea in a more principled manner and how we scale this to large networks. So the best way to show you the pipeline of BounceNet is through an example where here, this is a real example from our lab where we have the access points deployed across along a wall of the room, and the clients are deployed in the middle of the room. Now, the first step in BounceNet is the path discovery phase, where essentially you want to figure out all the paths between the different nodes in the environment. So all direct and indirect paths between all the different radios. Now, this is not too hard because the standard today already has a beam search phase that allows you to find all the different paths for a single link. We do, however, need to extend it in a way that allows us to do path search for multiple links in the network. And given that we found all the different paths in the environment, the next step is estimating which paths and links interfere. And to do this, we can essentially reuse all the measurements that were collected during the beam search, and we can estimate who interferes with who. And given that we have all this path information and the interference information, the next step is to figure out what is the best alignment of all these links in the end of all these links, such that you can densely pack as many clients as possible. So this is an alignment that was captured from a lab. So this is from a real experiment. And as you can see here, some of the clients are aligned along the line of sight path, so the best path, whereas other clients are sort of squeezed in by routing along the indirect paths in the environment. But while this does maximize the number of transmitting links for sure, there is still the question of fairness here, because typically reflected paths achieve much lower SNRs. So you're forcing some clients to always communicate on suboptimal paths. So to ensure that fairness is not completely broken, BounceNet also implements a fairness criteria where essentially it ensures that every client gets an equal chance to communicate on its highest data rate path. And to do this, BounceNet essentially generates multiple many-to-many alignments and switches between them, such that at least in few of the alignments, you can ensure that your client is well serviced at its highest data rate. But of course, there's the next question of mobility here, that as clients move around, things are going to change, paths are going to change, interference patterns are going to change. So how do you account for that? And to keep up with mobility changes, the entire pipeline here repeats every 100 milliseconds. So you can constantly keep getting the up-to-date information of where the clients are and how the environment has changed. Typically, given human motion speeds indoors, updating every 100 milliseconds works well enough. This is not an extra requirement from BounceNet. The standard itself today has this requirement that the beam search phase has to happen every 100 milliseconds. That's just how directional networks are designed. All right, so given this pipeline of BounceNet, in this talk, I'll mainly focus on the main technical block here. That is, how do you figure out the many-to-many alignment in the network? And to come up with the most optimal many-to-many alignment, we are going to model this. I should, Nilesh, can you unmute yourself and ask the question?
Yeah, can you hear me?
Yeah.
Thanks. So quick question, when you mentioned that the standard already has a way to discover the paths, who's the transmitter in that discovery process? Do the APs transmit, or do the clients transmit, and do the APs hear?
So both have to transmit, because you need to figure out the angle of departure from both nodes, right? So the way it works in the standard is first, the client will set itself to an omnidirectional mode, and the AP will start sending packets in each direction one by one. And then the client will say, hey, I heard you from so and so and so direction. And then the client repeats the same process where the AP becomes omnidirectional and the client starts sending in each direction. So the AP will figure out what directions the client can use to communicate. So it needs to happen both ways to figure out each sort of the direction from each side.
Okay, and one more, if I can. Do
Yeah.
the APs transmit simultaneously, or is it done sequentially, one by one in the
In
multi?
this case, it has to be done sequentially because again, like directional networks, carrier sense doesn't work. So if you don't sort of control this, there are going to be too many collisions and you just can't make sense out of it. So
Thanks.
so in a feature of our protocol is that sure APs are coordinated, but clients are not. Clients are all independent and distributed.
Thanks. Yeah.
Yeah. Okay. All right. So okay. So to generate many-to-many alignments, we are going to formulate this problem using conflict graphs. Now, conflict graphs are a very standard technique used in a lot of scheduling problems. Where essentially the graph represents the conflict for the scheduling. But in our case, to do the scheduling properly, we need to make sure that, so the scheduling is happening at the link layer, right? But to do the scheduling properly, we need to make sure that a conflict graph captures and abstracts out all the important information from the millimeter wave file layer. Information such as the multipath information in the environment, the antenna beam pattern imperfections and the leakages, and also the signal strengths of your different air paths. We need to formulate the graph in a way such that all this critical millimeter wave phi information is abstracted out and represented in the graph in some way. So let's say if I were to use the standard technique of implementing conflict graphs, right? One option is, the most common way to do it is have a vertex per node in the network. And now scheduling in such a graph becomes equivalent to picking vertices, that is picking nodes. I think there's a question from Samresh.
Yeah, hi. So, like in this beam forming thing, so whenever there is a new user, do you reiterate the entire process, or or you do it slot by slot basis? Suppose in every 100 millisecond you take the decision.
Yeah. So if someone comes in the middle, they have to wait till the next 100 millisecond beacon interval. They can't join in the middle.
Okay, thank you.
Yeah. Yeah. So in such a graph, the scheduling boils down to picking vertices, but that's not right for us, right? Like we're not trying to schedule nodes. We're trying to schedule links, that is alignments. So this clearly does not work for us. Another option is, okay, then maybe we could try to have vertices per link in the network. So corresponding to AP client 1, we can have a vertex pair 1 here. But this still is not good enough because this is sort of missing out all the multipath information in this channel. And all of this information is just getting reduced into the single vertex in the graph. So to make sure that all our multipath information is well preserved, we are actually going to formulate something called super nodes corresponding to each AP client pair. And essentially, each path that the AP client pair can use to communicate will have a corresponding vertex in the super node. So for instance, direct path DP has a vertex DP here in the super node. And similarly, any indirect path will have its own corresponding vertex in the super node as well. Of course, there could be more than one indirect path that the link can use to communicate, and each path will have its own corresponding vertex in the super node. So using this formulation, we can create all the vertices of a conflict graph. And as you can see here, this formulation preserves all the multipath information in our network. Next, we want to, right. That's the thing, because path loss is so high, you actually won't have as many reflected paths as you see at 2.4 gigahertz. Like 2.4 gigahertz, I completely agree. You'll have like secondary, tertiary, and all sort of multiple order reflections. In millimeter wave, you actually don't have too many reflections. You'll have only a few. Given firstly the directionality of the network and the high path loss, you'll only see reflections from metal cabinets, for instance, in our room. So because of this high path loss, you have only a select number of paths that you can actually now pick which path to send through. Like that is the whole sort of difference from 2.4 gigahertz. In 2.4 gigahertz, you can't really choose because almost every direction reaches your client. So this sort of sparsity in the millimeter wave channel is what allows you to formulate this problem in such a way. Right. So given that we've sort of come up with the vertices of this graph, the next thing is, how do we represent interference? We are going to represent interference using edges. So essentially this edge here means that we cannot route signals along this path and this path simultaneously. And we can represent the interference in the rest of the network using similar edges. And the important point to note is that the antenna beam pattern imperfections and the leakages are implicitly captured in the interference information in all these edges. Lastly, note that we don't want multiple paths to be picked for the same link. And as a result, you also have edges between the vertices in a single supernode. So you're ensured that only one path is picked for any link. All right, so this formulation captures all the multipath and all the interference information in a network. There's still one aspect of the physical layer it's not capturing, which is the SNR, that is the signal strength of all your different air paths. Yes, Nilesh.
All right. So I hope you can hear me. Yeah.
Yeah, I can.
You know, the way I'm thinking of the protocol you mentioned,
yeah,
essentially every path is nothing but a transmit receive beam pair.
Transmit receive?
Beam pair. So the AP
beam
would
pair,
have
sure,
a beam
yeah,
index.
That's right.
And the receiver would have another beam index, and essentially every ordered pair is a path. Now,
exactly.
What I don't understand is this mapping you do, for example, from DP of AP client pair 1 to the DP of AP client pair 2.
Yeah.
There seems to be some, I mean, how do you know that it's the same path based on
wait.
this?
Okay, AP client pair 2 are like AP2 client 2, so separate nodes, separate radios, and AP1 client 1 is a separate pair of radios. And DP essentially represents the line of sight path of each of these respective pairs. And this edge only means that I cannot transmit signals along these two paths at the same time, because maybe AP1 client 1 interfere, sorry, AP1 client 2 interfere, or AP2 client 1 interfere, or maybe client 1 client 2 interfere. Somebody in this pair interferes with each other. That's what this edge essentially represents.
I get that, but
yeah,
say in the protocol, for example, when the AP is sending out, a reference beam,
right?
How does AP2 know, for example, that how does that other AP client pair 2, for example, figure out that this is an interfering beam?
Right. So okay, so this actually goes into some of the specifics of how the protocol is designed. So today what happens in the standard is, if AP1 is doing the scan, then the standard only asks client 1 to listen. So client 1 can figure out what are the communication paths between AP1 and client 1. The thing that we do in our protocol, which is sort of the extra thing, is we not only make client 1 listen, we also make client 2, client 3, client 4, client 5, all of them listen at the same time. Listening does not add any extra over on the channel, right? But what listening allows us to do is, while AP1 is doing the scan, client 1 will figure out all the communication paths. But at the same time, client 2 and client 3 will be figuring out the interference paths. So what beams AP1 can use to potentially interfere at them. That is sort of how we make sure that without adding any extra measurement overhead, you can still figure out all the interference in the network, just by making sure everybody is listening when one guy is transmitting.
All right, thanks.
Yeah, that's a detail I did not cover in the talk. So yeah, fair enough. Okay, so I was talking about the SNR of all the different parts in the environment, and we will encode the SNR as the weight of the different vertices in this conflict graph. And by doing this, what happens is the expected data rate from any alignment gets automatically accounted for during the scheduling process. All right, so this formulation tells us all, sort of retains all the important physical layer information from the network. And now finding the best alignment from this boils down to figuring out the maximum weighted independent set on this graph. Now, of course, as we know, this is an NP-hard problem. And as the number of links grows, the graph becomes super dense and it becomes very hard to solve this problem. So how can we simplify it? To simplify it, our solution is based on the key intuition that first, your direct paths achieve higher data rates as compared to indirect paths. So what we want to do is, we want to prioritize scheduling links over the direct paths as much as possible. And towards this end, we essentially decouple the routing along the direct and the indirect paths, such that first we squeeze in as many links as possible along the direct paths, and then we try to fit in whatever links are remaining through their potential indirect paths. So coming back to this, our main sort of step is the decoupling step, where we create these multi-layered graph constructs, where we will first only consider the direct path conflict graph. And one of the things here is, notice that, Rajesh and Nilesh.
Rajesh here, if I may
Yeah.
go first.
I
So
think
how do
I
you know
can't hear him well.
how do you know something is a direct path?
Right, great question. I actually don't know that. I just look at whatever is highest SNR, that's the direct path. Because again, okay, one very important thing here is I am not mapping the environment in a geometric sense, right? The intuition is whoever is my best path, I want a fair share of that guy. So sometimes it's possible your direct path may be blocked, so your highest SNR is actually a reflected path.
Okay,
but that
fine,
still ties in with my fairness criteria, right? I want an
thanks.
equal chance on my best path.
I have a follow-up question.
Yeah.
So the this requires you to channel sound
Yes.
100 milliseconds for every transmitter and every
Absolutely.
and its intended receiver.
Yes.
Is this scalable?
To a certain degree, but you're right. The overhead is linear with number of links. So there is going to come some point where it just becomes absurd. I can tell you for 10 links, it is quite reasonable. This overhead is about 10%. But the important point is this is not any extra overhead compared to what the standard already requires. What the standard does today is if I have 100 milliseconds, it will break it up into 10 millisecond chunks. And it will say, hey, the first 10 milliseconds is just dedicated to link 1. Then 10 milliseconds dedicated to link 2. So it will just divide up and the overhead is not reducing because all the 20 nodes still need to do their scans. What we are proposing is, hey, let's rearrange all these scans and sort of make sure that at the end of these scans, we can get everyone to communicate at the same time rather than just not sharing the channel at all.
Okay, I sense that you're actually looking at working within the constraints of the standard. Okay.
Yeah, we are. Yeah, the being backward compatible was one of the sort of important design goals of this protocol. Yeah. Okay. Given that we decouple this graph, one of the things that we noticed is these graphs end up becoming very sparse, and as a result, empirically we observe that the resulting graphs that you get end up being caudal with a very high probability. Now, I won't get into too many details about what caudality is, but it essentially means that your graph does not have very large cycles. And you typically don't get very large cycles because the networks are very directional. And as a result, because of this property of caudality, the problem of maximum independent set actually becomes solvable in linear time. It is no longer NP-hard for this class of graphs. So given that this sort of decoupling step allows us to solve this problem in a more efficient manner, we can now figure out what is the best alignment of links that can densely pack as many clients as possible. And of course, not everyone can communicate along the direct path. So the remaining links are routed along indirect paths instead. So this is mostly, this is the technical details at a very high level. In the interest of time, let me move on to the results and show you the kind of experiments and the hardware testbeds that we used. So we evaluated BounceNet in a bunch of different rooms and locations with different kind of multipath characteristics, and also with a number of different hardware and radio equipment, each with different kind of antenna imperfections and hardware peculiarities. So these are the phased arrays at 24 gigahertz, which have a lot more antenna imperfections in terms of side lobes and all of that. These are horn antennas, which are perfect directional, but they can't be steered electronically. You have to steer them mechanically, which is not practical for a real system, of course. And for our main results, we show how the total network data rate scales with the number of links. And our first result is for the 12-degree phased array, which has the more realistic antennas that you would expect. And we compare BounceNet against two baselines. The first is the 802.11 AD standard today. This is the IEEE standard, which is mostly implemented in all commercial radios. And the second is a baseline where essentially we implement one of the state-of-the-art single link alignment schemes, and we allow every link to align independently, and then they just use carrier sense for medium access. And we refer to it as the baseline. Our main results show that both the standard and the baseline saturate very quickly in terms of total network data rate. And this is because either they don't account for interference, which means they end up having a lot of collisions and can't scale well, or like the standard, they just require too much time to detect and sort of account for interference. So it doesn't scale well. BounceNet, on the other hand, can scale the network throughput and achieves 3 times gain over both 802.11ad and the baseline. And this is primarily because with BounceNet, first, it can figure out the interference very quickly, and it knows how to sort of densely pack as many clients as possible without them interfering in the network. Yeah, Nilesh.
Sorry, very quick question. What's the physical MAC layer it's based on, your protocol? Is it AX or BE? Or
It's AD, so mostly OFDM.
yours is also based on AD?
Yeah, based on AD. Yeah.
Okay, thanks.
But yeah, but one thing is, like, we've replicated the phi of the AD, not the MAC of the AD.
Understood.
Yeah.
Yeah.
And we also have more results in the paper where we've shown that if you actually use narrower beams, like 3-degree beams, the gain from BounceNet can actually go up to 6.6 times. And moreover, if you look at the worst case client, the average throughput can increase by 13.5 times with BounceNet. This is because of two reasons. First, BounceNet naturally allows more links to transmit at the same time, but also because it has this fairness criteria that makes sure that clients that would have otherwise suffered from a lot of interference are not as worse off in BounceNet. All right, I think I'm should be at the end of my time limit, right? Okay, I have 10 minutes. Okay, all right. Then I'll quickly just talk about one other project here. It's a hard deadline, right? It's a hard stop. Okay, perfect. Okay. Okay, then the next project I will talk about is ISLA, where essentially the goal is how can you use the large bandwidth of 5G signals to localize IoT devices in the wild. And we want to do it in a way that does not require any coordination or synchronization with the 5G base stations. So the number of deployed IoT devices is exploding, and it's being used for a number of different applications, such as smart city monitoring, data-driven agriculture, and smart factory automation. Surveys project that the number of deployed IoT nodes is going to grow to about 31 billion by 2030. And with such ubiquitous deployment of devices, the ability to localize and track these with high accuracy is going to be very, very important going ahead. So the most common outdoors localization technique used today is, of course, GPS. But the issue with GPS is it is very power hungry, and several studies have shown that GPS can consume almost the same power as the entire IoT device. So it cuts the battery life in almost half. And second, it also comes with extra hardware costs, of course. So as a result, past research has tried to use cellular networks or dedicated IoT base stations to help with outdoor localization. But the challenge is they either achieve very low accuracy and are only good for coarse-grained estimates, or they require active participation of the base stations to jointly localize the IoT device, for which they first need to tightly synchronize the base stations with each other to support localization. And this is actually very impractical because now the cellular company has to step in and modify these base stations to support localization, which would just never pan out. So rather than going down that route, the main question that we're interested in here is, can the IoT device accurately localize itself by first only listening to ambient 5G signals in the air, and two, without requiring any coordination or modifications to the 5G base stations. And this aspect of ambient localization is actually really, really important to the scalability aspect of the system, because note that we expect IoT devices to be deployed in the millions tomorrow, whereas we are going to have much, much fewer base stations. So the fact that the base station does not have to allocate dedicated time frequency blocks for localization really helps with the scalability aspect of the system. So 5G presents some very unique opportunities that allows for high accuracy localization. The first is the small cell architecture in 5G will lead to a very high density of deployed base stations, which means we have many more anchor points to give us high accuracy. And second, 5G packets can span very large bandwidths, up to 100 megahertz below 6 gigahertz frequencies. And in the millimeter wave, this can be actually as high as 100 megahertz. And the advantage of high bandwidth is it gives us very high resolution in time of flight. which will in turn allow for very high accuracy localization. To see this, consider this scenario here, right? Where you have a 5G base station and a 5G compatible device, and there are 3 paths in the environment. One is the line of sight path at 11 meters, and you have 2 environmental reflectors at 15 and 39 meters. So after the mobile device captures the 5G packet, it can use the information from this packet and translate it into time of flight information. This essentially tells you the distance traveled by each path in your propagation environment, right? And because with 5G, you have very high resolution in time of flight, you can see that we can actually separate out the distances traveled by each path because of the high resolution. And that allows us to accurately estimate the distance traveled by just the line of sight path. So what we could potentially do here is just collect the line of sight path information from a bunch of different base stations and use that to localize the IoT device, right? However, the issue is that making use of the same opportunities on low cost IoT devices is very, very challenging. And the reason is IoT devices typically have low speed and low cost ADCs, that is analog to digital converters, which means they can only capture a very narrow bandwidth. They can't capture the entire 100 megahertz signal, right? In our case, the IoT device has 16 times smaller bandwidth, which means it can only capture this narrow portion of the spectrum, 100 by 16 megahertz portion here. And this in turn means that its time of flight resolution is also going to be 16 times worse. So now what does that mean? If the IoT device captures this packet, the corresponding time of flight domain representation will be completely merged. You just won't have the resolution to separate out the different paths. And now the IoT device can't estimate what your line of sight path distance was. So this is a big problem. But of course, there's also the second challenge, right? That given that you're only using one-way measurements, the time of flight that you're estimating from these packets are always going to be corrupted by synchronization offsets, because your base stations are not synchronized at the clock level. So this means that you always have an offset that you can't correct for. So using only one-way measurements, how can you actually localize the IoT device without any coordination with the base stations? So towards this end, in this project, we present ISLA, which stands for IoT self-localization using ambient 5G signals. And ISLA is made up of 2 components. The first is how are you going to capture the large bandwidth of 5G signals on your narrow bandwidth IoT devices? And second, given that you captured this bandwidth and you recovered the time of flight, how can you actually use this bandwidth to localize the IoT device without coordinating with the base station at all? So in this talk, I'll mainly focus on the first part, the first technical portion over here, but I'm happy to take questions about what we did for the second part as well. All right, so how do you capture large bandwidth 5G signals on narrow bandwidth IoT devices? To do this, we are going to leverage recent advances in RF circuits that allows us to use MEMS acoustic resonators to design new kinds of RF filters. So what do I mean by this? If you look at traditional RF filters, you mostly have either low pass filters, which keep the low frequencies, filter out high frequencies, high pass filters, which filter out low frequencies, keep the high frequencies, or band pass filters, which keep frequencies within a band. However, with MEMS filters, we can now design something called RF spike train filters, which essentially is a sequence of periodic spikes across a large bandwidth. This is the filter response, and this is the corresponding image of the filter under a microscope. And now what this allows us to do is we can keep tiny portions of the frequency across a very large bandwidth. And this is a new capability that such filters give us. So how can we use this to achieve our goal of high resolution localization? So the crux of the problem is that 5G signals are high bandwidth, but our IoT devices only allow us to capture this narrow bandwidth here. So how do we get around this limitation? The key intuition is that we will first pass the 5G signal at the input of the IoT device through this MEMS spike train filter. As a result, what will happen is the spike train filter will only allow certain frequencies to pass, but it will suppress all the other frequencies in the signal. Now, if you look at this, it is almost like we took samples of the frequency. We took frequency samples across the signal, which is equivalent to subsampling the signal in the frequency domain. And by doing that, you can see that the signal becomes sparse in frequency. Now, if you're aware with sparse recovery or compressive sensing, this should sort of ring a bell, where sparse recovery essentially tells us that if your signal is sparse in frequency, in the frequency domain, then you can actually subsample the signal below the Nyquist rate and still recover it perfectly, right? So now over here, let's say that we have this 100 megahertz signal, but we have an IoT device that's sampling it 16 times below the Nyquist rate of this 100 megahertz signal. What would happen? What would happen is we would get something called aliasing, where aliasing essentially tells you that you had this broadband 100 megahertz signal, but you've subsampled it by 16. So you're only left with this 100 by 16 megahertz chunk now. And all the frequency components that fell outside this narrow band after aliasing will map and fall somewhere inside this narrow band. So at the end, at the output of the IoT device, what we are able to observe is only this narrow band chunk where things from outside have fallen in. Our goal is, looking at this alias spectrum, can we recover back the original broadband spectrum that we had here? And if we can do that, we can use it to recover the high resolution time of flight of the environment. One very important point here is the time of flight that we can measure is actually the exact same resolution as if you had captured the entire 100 megahertz signal. And this is because your resolution and time of flight at the end of the day depends only on the end-to-end bandwidth of your frequency measurements. And it does not require you to have every single frequency measurement in this bandwidth. In fact, ironically, if I gave you even just the first measurement and the last measurement, technically your time of flight resolution is just as high. You lose out on something else, which is the maximum unambiguous sensing range, but resolution depends only on end-to-end bandwidth. So this is the key intuition of how we can use these MEMS spike train filters to be able to retain the resolution and time of flight. Of course, there are a lot of system level challenges on getting this to work properly. In fact, our first big problem was at the sparse recovery step, where essentially you could have a situation where after aliasing, different frequency components collide in the narrow band. So how do you resolve it? A lot of past work on compressive sensing uses co-prime subsampling factors to deal with it. But in our case, we can't do that because given the OFDM structure of this input packet, if we don't sample it by anything that is not a, okay, this is getting, okay. Your OFDM signal has some number of subcarriers, right? Let's say it is N. In the paper, we showed that if you subsample this N subcarrier signal by anything that is not a proper factor of N, then your orthogonality breaks once you subsample the signal. So let's say the OFDM packet has 1024 subcarriers. You can only subsample by 2, 4, 8, 16, and so on. If you subsample by 3, orthogonality breaks here, and you can no longer recover time of flight. So the point is, as a result, we couldn't use co-prime subsampling factors, and we had to use other techniques of designing the MEMS spike train very carefully to make sure that collisions don't happen. Anyway, these are very sort of in-depth technical details, and I'm happy to talk more about this at the end. But let me just quickly wrap this project up. So this is the spike train filter that we built in our lab. And here is the corresponding filter response of this filter. And as you can see here, if I subsample this filter by 16 times, this is the aliasing pattern we get here. And the key thing here is you can see that none of the spikes collide. They're all separate, which means that sparse recovery is equivalent to just rearranging where these spikes came from, because I'm getting very clean channel measurements, given that no one is colliding. So for our main evaluations, we tested, so we used this filter to build a prototype circuit and a prototype 5G base station, because the town I come from in the US is a very small town and there's literally no 5G deployments there. But we also tested in a bunch of different environments where one was a campus test bed with a lot of multipath effects and so on, and a stadium parking lot and a huge agricultural farm spanning around 1 kilometer. And for our main results, we essentially show the localization performance of an IoT device with and without ISLA. Now, without ISLA, the IoT device can only capture a very narrow spectrum, which means it doesn't have any resolution in time of flight, right? So its performance is quite bad. However, with ISLA, by using the MEMS spike train filter, we can now allow the IoT device to sense a wide bandwidth, which gives it very high resolution in time of flight and can in turn improve the localization performance by 3.35 times. And note that both these baselines were using the same IoT hardware with the same low power ADCs. Apart from the MEMS filter, which is a passive component, we don't have any extra hardware here. Finally, we also compare against a full 100 megahertz receiver, where essentially it's a baseline where your receiver is a broadband receiver and can capture the entire packet. And over here, you can see that the performance of IoT with ISLA and the full 100 megahertz receiver is very close. This is because time of flight resolution depends only on end-to-end measurements and not on having all the measurements. And we also measured compute these performance in all our different test beds, and we see similar results. And the main takeaway here is that ISLA can achieve a low-cost, narrow band IoT receiver to achieve localization performance equivalent to having a full 100 megahertz receiver, despite the fact that the IoT device is subsampling the signal at 16 times lower rates. So this is a summary of my talk. I think I may have sort of gone beyond by a, oh yeah, okay, 5-3, I'm not too bad. Anyway, yeah, so any questions? I'm happy to take questions at this point. Yeah, Nilesh.
Suraj, one thing about the ISLA setup.
Yeah.
So your front-end bandwidth, even after the spike filter, will have to be 100 megahertz.
Front-end bandwidth is always 100 megahertz, right? It's only before the ADC that you put an anti-aliasing filter, which limits the bandwidth. In our case, we just remove the anti-aliasing filter. We allow aliasing to happen because at the end of the day, our ADC is what defines the main bandwidth of the radio RF chain.
I see.
Yeah,
All
but
right.
analog components have 100 megahertz bandwidth. That's not the big issue.
All right.
Yeah. Yeah.
How does the OFDMA based connection and multiple access
Right.
fit into the setup?
Right. That's a very good question. So OFDMA is more like a kind of channel access scheme where different clients choose different subcarriers of the packet, right? That also could be incorporated into BounceNet. So essentially that is scaling across the frequency dimension, right? Where you're dividing frequency across clients. I guess in BounceNet, the goal is let's keep everyone on the same frequency, but how much can you push the scaling across the spatial dimension? And we sort of limited the study just to scaling across space rather than scaling across frequency or time.
So, in this MSA work, do you have still have frequency selective trading?
Yes, you do. Yes, you do. You do. Oh, okay. It's kind of tricky because frequency selective trading happens because of multipath, right? It's like there are two paths which at different frequencies they add up either constructively or destructively. Multipath trading happens a lot more when you have omnidirectional transmissions where signals are technically going everywhere. Let's say I had a perfectly directional antenna that was almost as narrow as a pencil. I won't have frequency selective trading because there are no multiple components to add up. In real life though, your antenna patterns are not perfect. You'll have side lobe leakages. The beam itself will be quite wide. So you can have multipath components sometimes. And when that happens, you have frequency selective trading. Any other questions? About any of the other projects is also, I'm happy to take questions. Thank you so much.